Here we have a capacitor. It's a pretty big capacitor with 1,000 farad. So what exactly is a farad? Now, by defining capacitance, we say capacitance occurs when two conductors or plates are separated by a dielectric or insulator. So I can literally draw a capacitor as two parallel plates, and each plate has an area of A and separated by a distance of D. In between, you have a dielectric that has a dielectric constant of epsilon, and the voltage across the capacitor is V, and also each of the plate will store, in this case here, a charge of Q. Now, as defined in this equation, the capacitance is defined by the equation Q, which is the amount of charge you can store on either one of the plate, is proportional to the capacitance of the capacitor multiplied by the voltage V. Or in other words, C can be defined as the amount of charge that the capacitor can store per unit voltage. So here, this term, the unit here is farad, whereas this term, Q, the unit here is coulomb, and this is voltage, volt. Now, on the other hand, we can also look at capacitance from the amount of energy stored in the electric field. So the energy stored has a density of 1/2 of epsilon times E squared, where E is the electric field and epsilon is the dielectric constant. Now we learned early on that the electric field E is equal to the voltage divided by the distance. So if you look at the total amount of energy, W, that is stored between the two capacitive plates, is equal to the energy density, which is 1/2 of epsilon E squared. That's for each of the point in space, the energy density is 1/2 epsilon of E squared. But the total volume of the space between the two capacitor plates would be equal to A times D. Now, if you substitute the first equation into the second equation, you get something like 1/2 of epsilon V divided by D squared times A times D, which if you collect the terms, what you have is that this is equal to 1/2 of epsilon A divided by D times V squared. This is the amount of energy that is stored by the capacitor. Now, later we're going to show that the energy stored by a capacitor is also given by the equation of 1/2 of C times V squared, where C is the capacitance of the capacitor. So if you compare equation 3 and equation 4, you basically have C equal to epsilon A divided by D. And so the capacitance of a capacitor, first of all, is proportional to the area of the capacitor and inversely proportional to the separation of the plates and also proportional to epsilon. So if you look at this capacitor I have on the hand, this is called a coil capacitor, for which you have a very large amount of area, literally a screw of two parallel plates, and separated by a very small distance D, several millimeter across, and then they coil the parallel plate into a tightly wrapped coil, and then stuck in there, and then put the one terminal on the positive plate and the other terminal on the negative plate.